Okay, let's dive right into this. Welcome to today's Explainer, where we are embarking on a highly focused, intensive walkthrough of the Cambridge IGCSE Additional Mathematics Review chapter. If your goal is to absolutely maximize your mark potential, sharpen your mathematical agility, and bulletproof your exam strategy, you are exactly where you need to be. We're going to break down real multiple choice questions, algebraic manipulations, and function concepts into crystal clear, logical steps. We'll be looking at exactly where students tend to drop marks and how you can avoid those exact traps. So grab a notepad, get yourself comfortable, and let's decode some serious math. Here is the game plan. We are tackling 5 distinct thematic rounds today. Round 1, numerical operations and indices. Round 2, expanding and factorizing. Round 3, rearranging and solving equations. Round 4, geometry and bearings. And finally, round 5, evaluating functions. Section 1, numerical operations and indices. Let's get straight to it.
All right, here is our first challenge pulled straight from the review chapter. The question asks us to evaluate 3 to the power of 3 multiplied by 3 to the power of -5, giving your answer in index form. Now, the command words here are absolutely crucial. Evaluate means we need to process the operation, but giving your answer in index form is the catch. It means the examiner does not want you to write out the final decimal or fraction. They want to see the base and the power. So take a second. Pause the explainer if you need to. Think about what the standard rules of indices tell us to do when we are multiplying terms that share the exact same base number.
Okay, let's look at your options and lock in a final answer. Is it A, 9 squared, B, 9 to the power of -15, C, 3 to the power of -15, or D, 3 to the power of -2? Look very closely at how the bases and exponents are interacting here. And hey, while you're thinking about which trap you might be falling into, let me drop a quick reminder. Subscribe to our YouTube channel, Ace the Exams, at Ace the Exams IGCSE to excel in your Cambridge examinations. Hit that button right now. All right, do you have your answer? Let's break it down. And this brilliantly illustrates the fundamental rule of multiplying indices. The correct answer is D, 3 to the power of -2. Let's talk about why. When you are multiplying terms with the exact same base, in this case, the number 3, you simply add the exponents together. That's the rule. So a +3 plus a -5 leaves us with an overall exponent of -2. Notice that the base stays exactly the same. A massive trap students fall into is multiplying the base numbers, 3 times 3 to get 9. No, the base just carries over. Understanding this core mechanic is absolutely critical because index manipulation is the foundation of almost all the higher-level algebra you're going to face.
Section 2, expanding and factorizing. Time to level up into algebraic manipulation.
Here is your next prompt. Fully factorize 15x squared y plus 25xy squared. Notice the word fully there. That is a massive hint from the examiner. If you just pull out one common factor but leave others inside, you will not get full marks. You need to identify the highest common factors for both the numerical coefficients, the numbers at the front, and the variables across both terms. I'd highly suggest pausing here. Take it step by step, look at the numbers first, then look at the x's, then look at the y's. Pull out the largest possible pieces you can.
Let's see how you did. Start with the numbers 15 and 25. The highest common numerical factor there is 5. Okay, boom, pull that out. Next, look at the variables. The first term has an x squared and the second has a single x. The most we can pull out of both is just one x. Same logic goes for the y's. The first term has a single y and the second has y squared. The most we can pull out is a single y. Put it all together, and our overall common factor sitting outside the bracket is 5xy. Now what's left inside? Divide the original terms by 5xy. 15 divided by 5 is 3. X squared divided by x is x. And the y cancels out. So the first term inside is just 3x. Apply that same logic to the second term, and you're left with 5y. Therefore, our fully factorized perfect score answer is 5xy, open bracket, 3x plus 5y, close bracket. Section 3, rearranging and solving equations. This is where we test your structural agility. Your task here is to rearrange the equation y equals, in brackets, x minus 5, all divided by 5. The goal? Make x the subject, meaning we want to find a line that says x equals and then everything else on the other side. This is like untying a mathematical knot. You have to work from the outside in, doing the exact inverse operations. Grab your pen, pause the explainer, and isolate x. And while you're working on that,
stop scrolling for a second. Subscribe to our YouTube channel, Ace the Exams, at acetheexams_IGCSE to excel in your Cambridge examinations. We want you hitting those top grade boundaries, so make sure you're subscribed. Okay, let's look at how to untangle this formula. Let's look at the options you might have ended up with. To solve this efficiently, target the biggest structural obstacle first, which is that fraction. The entire right side is being divided by 5. What's the inverse of dividing by 5? Multiplying by 5. If we multiply both sides by 5, the fraction disappears, leaving us with 5y equals x minus 5. We are so close now. The only thing keeping x from being by itself is that pesky minus 5. Which confirms the correct answer is option D. If we just add 5 to both sides, we completely isolate our variable. The minus 5 vanishes from the right, and the left side becomes 5y plus 5. So x equals 5y plus 5. If you chose option D, you successfully and perfectly manipulated the equation. It is literally just about performing the exact same logical operation to both sides of the equal sign, until your target variable is the only thing left standing. Section 4. Geometry and bearings. Let's shift our cognitive focus over to spatial reasoning and shapes. Now, what's really interesting about this specific exam question is how it forces you to layer multiple concepts together. We aren't just plugging into one formula, we have a sequence to follow. We have an isosceles triangle with a base of 10 centimeters and a total area of 60 square centimeters. Our ultimate goal is to find the perimeter. Remember, perimeter is the total distance around the outside edge. To get there, you have to work backward. You must use the area and the base to find the vertical height first. Once you have that height, if you drop a line straight down the middle of that isosceles triangle, you split it into 2 identical right-angled triangles. From there, you use Pythagoras' theorem to find those missing slanted sides. Pause the explainer. Try to run through those 3 steps right now. Did you get it? The final perimeter is exactly 36 centimeters. Let's walk through the strategy. The formula for the area of a triangle is half the base times the height. Half of our 10 centimeter base is 5. So 5 times the height equals our area of 60. Divide 60 by 5 and we find our vertical height is 12 centimeters. Great. Now look at just one of those right-angled triangles we made. Its base is 5, its height is 12. We need the hypotenuse. Pythagoras tells us a squared plus b squared equals c squared. So 5 squared is 25, plus 12 squared is 144. Add them up, you get 169. The square root of 169 is a perfect 13. That means our 2 equal slanted sides are 13 centimeters each. To find the total perimeter, add the 2 sides in the base. 13 plus 10. Boom, 36 centimeters. Absolutely brilliant if you manage to chain all those concepts together. Next up, let's test your directional reasoning. The bearing of Zurich from London is 126 degrees. Find the bearing of London from Zurich. This is what we call a reverse bearing challenge. Remember the golden rules of bearings. They are always measured from north, they are always measured clockwise, and they are always written with 3 digits. I highly recommend you pause here. Draw 2 dots on a page, draw parallel north lines going straight up from both, and physically sketch out the angles. It makes all the difference. The correct reverse bearing is 306 degrees. Here is the ultimate exam hack for reverse bearings. Because bearings are measured clockwise from parallel north lines, finding a reverse bearing when your original angle is less than 180 degrees is incredibly straightforward. You literally just add 180 degrees to your original bearing. That's it. 126 plus 180 gives us the perfectly reversed direction of 306 degrees. If the original bearing was over 180, you just subtract 80 instead. It's a fantastic time-saving rule of thumb that beautifully illustrates how interior angles and parallel lines function in real-world navigation. Section 5. Evaluating functions. We are moving into our grand finale, focusing on mathematical mappings and domains. I want you to imagine a mathematical function as a factory machine. The crucial point is understanding how an input value gets systematically transformed into an output value. Here we have a set of inputs: 1, 9, 25, 49, and 81. Our factory machine's rule is simply the function f of x equals the square root of x. When we feed these inputs into the machine, they map perfectly to their positive square roots. 1 becomes 1, 9 becomes 3, 25 becomes 5, 49 becomes 7, and 81 drops out as 9. It's a perfectly clean, predictable relationship. But machines have limits, right? Looking at how this specific square root function operates, here is a critical thinking question directly from the source material to test your understanding of domain restrictions. For this square root function machine, what types of numbers absolutely must be excluded as an input? Think about the fundamental limitations of calculating a square root within the standard real number system. What would literally break the machine? The resolution here is that any numbers less than 0 must be strictly excluded. In standard, real number mathematics, you simply cannot process a negative number through a square root function machine. Why? Because a positive times a positive is positive, and a negative times a negative is also positive. There is no real number you can multiply by itself to get a negative result. Attempting to input a negative value will not yield a real output, which means negative numbers are invalid inputs. They are outside the allowed domain for this function.
Let's pose one final, thought-provoking question to wrap up today's session. Look very closely at the outputs of square numbers. Whether you're squaring 1, 2, 5, 10, or 100, there is a pattern. Which single digits will never ever appear as the final digit of a perfect square? Try to visualize the first 10 square numbers in your head right now to see if you can spot the missing digits. Let's see if you caught it. The answer is that no perfect square will ever end in the digits 2, 3, 7, or 8. Think about it. 1 squared is 1, 2 squared is 4, 3 squared is 9, 4 squared is 16, which ends in 6, 5 squared is 25, ending in 5. No matter how massive the number gets, perfect squares only ever end in 0, 1, 4, 5, 6, or 9, never 2, 3, 7, or 8. This is an incredibly handy mathematical property to keep in your back pocket to quickly spot and rule out invalid numbers on a multiple choice paper. And that brings us to the end of this intensive review. So I want to leave you with this question. Which mathematical round challenged you the most today? Was it visualizing the reverse bearings, pulling out those algebraic factors, or trying to combine the area formula with Pythagoras? I highly encourage you to go back and review the specific concepts that made you pause the longest today. Tackle those weak spots head on. And before you go, remember, subscribe to our YouTube channel, Ace the Exams, at acetheexams_IGCE to excel in your Cambridge examinations. Drop a comment below with the biggest challenge you're currently facing, and keep that focus sharp. See you in the next explainer.